Hello and welcome to the first video of Chapter 9. This is multiple regression. Let's get started. All right, these of course are whales, and whales were hunted once for their oil, which is not a great thing, and great scientists found that the metaphone plant would actually produce a similar oil with similar qualities, and here is the metaphone plant. There is the flower it produces, and there is the wonderful byproduct of the oil that has the great properties. What we wanted to do, or what a scientist once did, was to see if certain factors affected the flowering of this plant, which was associated with the oil. So it's going to measure the number of flowers that come out of this plant. That will be our response variable. And it wanted to know if factors such as the intensity of the light or when we start applying light actually increases or decreases or has an effect on the number of flowers in that plant. And this is the case study from Chapter 9. And when you read that, I'll trust you've read it, but I'll just kind of review it. We started off with 120 seedlings transplanted into individual pots and randomly assigned to 12 treatment groups. The 12 treatment groups are, of course, there are 6 light intensities, and there are 2 times at which we apply the light. Once in the early stage and once in the late stage. The early is before, if you notice this, this is at 8 hours. We're applying it for 8 hours a day, whereas here we're applying it for 16 hours a day. That's known as the PFI. That's when they think when they increase the light time, not the intensity, but the amount of exposure from 8 to 16, that's when the bulb is supposed to open. So this is before what's called PFI, and this is late after PFI, and this is the varying amounts of intensity that are given to it. So that is the experiment, and here is the data. I just want to look at the data, and we'll probably see it and have to clean it up a little bit before we put it into SAS, but this is the, or R or Python or wherever whatever program we end up using. But here is the data. You can see that 1 is associated with late, and 0 is associated with early. That's going to become important to us a little bit later, whether we're running proc reg or proc GLM. We'll see how that how that gets handled in a minute. But here is the data, and that is light intensity on the x-axis here, and up and down on the rows, or on the columns is light intensity, and on the rows is timing. This experiment was repeated twice. What you're seeing here are the 10, or the average of the 10 plants, and then they ran at each level, 150 at the late or 150 at the early, and they ran the experiment twice with similar results. And if we just add across timing, we forget that timing even existed, we would have 4 observations across 150, a light intensity of 150, or across all light intensities. And so this is simply, since they're all balanced, right, there were 10 in each group here, we're going to average across all of these 4 to get 73.27, and so on and so forth for all these. And looking at that, we can see that it looks like as light intensity increases, there might be a trend that the actual average number of flowering decreases. But that's what we're going to test here with our multiple regression. So this is what we might want to do first. Let's forget about timing altogether. Notice that timing is not in the model, and we've got a simple linear regression model here. We've got our plot, which will be output from proc reg or proc GLM. We can look at the residual plot. We don't see too much against the assumptions here. And we'll go over those again here in a minute as a review. But here is the SAS code that we use. We use proc reg. And there's a couple of, obviously there's a lot of things to get out of here. But right now we just want to look at the intensity. And it looks like indeed there is some evidence of a negative correlation, negative linear correlation with the flowerings, the average flowerings, and the intensity. And that is indeed significantly different than 0. So that is something interesting for us to look at. Another thing that's going to be interesting for us to look at, we know how to interpret all these other R-squareds, goodness of fits, and but the thing I want us to look at is the MSE, which is right here, the mean squared error of 79.9. And we know that these betas down here are unbiased. We know that the MSE equals the variance plus the bias squared. So since they're unbiased, that bias is 0, and so this MSE actually reflects the variance in this model. So I could look at the root MSE, and that would be an estimate. That's sigma hat, whereas this is sigma hat squared. That's sigma hat, and that's an estimate of the standard deviation of, since we're assuming the standard deviations are equal, that's an estimate of the standard deviation of flowering, of flowerings for a given intensity level. So, what do we want to do next? We said, well, maybe we can learn something from the timing. So we'll add the timing on there. We look at the timing, and we're just simply averaging across all of the ones that were late and all of the ones that were early to get the marginal values here of the timing. And it looks at, like, the early is 62.2 and the late is 50.8. We could run a two-sample t-test on this, right? Or we can equivalently do that in a regression. And that is what we wanted to do next. We said, well, it looks like we might learn something about the mean flowering based on light intensity and flowers. Looks like there might be something to this. So that is what we wanted to do here, looking at metafoam, light, and time. Now we're putting light and time into the model. And we see here, again, we're just reviewing, but this is how we would do it in the SAS code, procreg, data equals MF, that's metafoam. And that is the data set that we had. And here is models, flower, intensity, time. Remember, if you were using procglm, you would have a class statement in here, like we'll see later, and you'd have a slash solution out here. You get the same exact results. Looks like intensity and time are both significant. This will give us two different lines. So we'll have two different lines here, and this here should be, and it'll be in future ones. Did I actually do it? I put that in there. So this says 1 and 2, but the time, the top one is red, that's early, and the bottom one is blue, that's late. So you can think of the red ones here as 0 and the blue ones as 1. I'll have that fixed here in another slide. But that's what we wanted to see, is that these slopes are forced to be the same. We're not allowing ourselves to have different slopes, but we are allowing ourselves to have different intercepts. And that's what we're doing here with procreg. And when we put time into the model, it's just putting in a 0 for early, and it's putting in a 1 for late, and treating it like any other number. But when what that's happening is the red ones up here are when it's 0, and the blue ones down here are when it's 1. So the intercept, so what is this telling us? It's telling us, well, for the 0 ones, there is no adjustment. For the 0 ones, whatever the intercept is, will be the intercept of the early, of the regression for the early seedlings, the seedlings that were given the light intensity early. Now, when we have the late one, that's what this coefficient means right here. And I really like procglm better. I think it does a better job in this parameter estimate table of showing us this. But if we know how to interpret it, we can get it from any parameter estimate table. This one's just saying, hey, the adjustment to this slope of 83 for the early is minus 12. And so since the slopes are assumed to be the same and are here forced to be the same, we know that the distance for any value of light across here is negative 12, or just the distance is 12.15833. And so that's how we get it. This number here is the adjustment to the early to get the late. The adjustment to the early intercept to get the late. And notice that both lines have a slope of negative 0.04047. And most importantly, or equally importantly, we know that those are all three significant. This number will never really be 0. The question is that a significant adjustment? And this one is seen to be a significant adjustment for time. So it looks like the flowering is, that we can model the mean flowering using both intensity and time, and that flowering, the mean of the distribution of the flowerings is indeed dependent on both time and intensity. So I'm going to leave that off here for this first one, and we'll pick up, this is a good place to stop for this moment. We're going to pick up and look how to do this in procglm, and a few more, look a little deeper into this example on the next set of videos. Coming back at you next. All right. Hello and welcome back to part 2 of chapter 9 for multiple linear regression with a categorical variable. Our categorical variable here, remember, was time. Its coefficient here is beta 2, and we ended with the fact that it has two different levels, early and late, and so we have two different regression lines, which of course here looks like they're parallel so that they share the same slope, and you can see that slope here at the intensity parameter of negative 0.04047. So they're forced to have the same slope, but not forced to have the same intercept. And so if we're using proc reg, whatever's coded as 0 will be the reference. That, of course, is early, so that it takes on the intercept, the straight-up intercept of 83.46. That is the intercept of this red line. And then we get the adjustment of that, and that is when time is 1, which is late. The adjustment is negative 12.15883, or 833. That is 83 minus that 12, which will give you about 71.3. And that difference of negative 12, or the difference of 12, is consistent throughout all light intensities because the slopes are forced to be parallel here. And that's what we see down here. That's where we left off last time. Let's continue, though. I've had this question before of how is this different than if we just ran two separate regressions, one on the early and one on the late. Of course, if you just ran it on the early, you'd be running it only on half the data. You can kind of see that up here. We're only running it on 12 of the data points up here and 12 over here, whereas I'm using all 24 over there. More data you have. We're assuming that whether it's early or late, remember we're assuming that they have the same standard deviation, that those flowering have a normal distribution with the same standard deviation, but not necessarily the same mean. And we're seeing that reflection in that adjustment, that significant adjustment of negative 12 to the intercept. But you can see that here. The whole point is that notice that right here, this is just some SAS code introduction of kind of filtering. So where time equals 0, this one's where time equals 1. So this is all the early data. That's all the late data. Notice that those slopes are different. And when I use all the data together, the slopes are they're all somewhat a little bit different. That's just because it's different data. You can see that reflected also in the degrees of freedom for the error term. So you can see that these are 10 because these are simple linear regression models with two parameters, intercept and a beta 1 for intensity. So that's the initial 12 minus 2 is 10. Over here, the same thing, 12 minus 2 is 10. But here we've got 24, and to get that 21, notice that we're regressing here on intensity and time. That was our full model using both. That's a beta naught for the intercept, a beta 1 for intensity, and a beta 2 for the time variable, and so that's 3 parameters. 24 minus 3 is, of course, 21. So that's just another big review there, and we want to use all of the data if we can assume the standard deviations are the same so that we can get a good estimate of the MSE and thus the variance of the model. So, so let's keep going with our case 1 study here for metafoam. This is from the book, so we're just kind of relating what you'll see in the book to what you see in SAS. So I'll keep going. Remember, the early line has a higher intercept. You can see that intercept up here. Moving on, just kind of reviewing the assumptions of the models. Remember that no matter where you are, no matter what combination of light intensity and no matter what combination of light intensity and time, we're still assuming that if we could see, if we repeated this experiment, we repeated it twice. Let's say we repeated 1,000,000 times for each light intensity and time combination. We wouldn't get the same mean flowerings each time. And we're saying that we're assuming that those mean flowerings will all have normal distributions with the same standard deviation, but possibly different mean. And it's that mean of that normal distribution that we are, that we're estimating, that we are trying to learn about through this regression. That is our response. So, moving on. That is the idea. Just a couple things to remember. Interpretation is more straightforward. The reason why we want to have equal standard deviations is it's more, it's more straightforward when the inference is on only the mean rather than one of the parameters, more than one of the parameters of the response distribution. All we're saying here is that there's two parameters of the response distribution, the mean and the standard deviation. It's nice when we can assume the standard deviations are the same, so we only think that the things that might be different between these distributions are the mean. And then finally, constant variance is an assumption of the tools that we're going to need in Chapter 10, because that's where we're going to start looking at confidence intervals for linear combinations, trying to get standard errors for linear combinations of these betas to really extend our ability to answer more questions of interest and build more confidence intervals for not just parameters, but linear combinations of these parameters. But remember, as a mathematical statistics point, the parameter estimates are still unbiased. These are OLS estimates. They're unbiased even if we have non-constant variance. It's only the standard errors of those that, that may be inconsistent, not the expected value of the parameter estimate. So, keeping going. In fact, I'm going to take a break there. So come on back for part 3, and I'll see you in a moment. All right, adios. Hello and welcome to part 3. We left off last time looking at the assumptions of the multiple linear regression model. As we know before, here we have a categorical variable and again a continuous variable of light intensity and the categorical of time. When we interact those, we've got, well, not interact those, but the that gives us 12 different possible treatments, one for each light intensity, and for each light intensity we have 2 different times, early and late. And we're saying that the flowers have a normal distribution with the same standard deviation no matter what the combination of light and time, except possibly different means. And these are unbiased estimates. Whether the assumption of equal standard deviation is met or not, the betas are still unbiased estimates, meaning that the MSE is still the measure of the variance of these, the variance of the model, which is, of course, here sigma squared. So that's going to become important when we hit up chapter 10, and in chapter 10 we'll be again finding different confidence intervals for linear combinations of betas and other exotic statistics that that we will need to know. We'll need to be able to get a good estimate of the MSE to do, and we'll be depending on this constant variance. So let's look at a breakdown though of what we've been talking about so far. And so in our model here, we have beta naught, beta 1 light, beta 2 time. Time is a categorical variable. We're treating light as a continuous variable. And we have the breakdowns here. So we've seen all this before. This is really what's going on. This is what I think really kind of brings it all together. So we're modeling the mu, the mean of flowers, given, right, the bar here, given light and time. And at time equals 0, this is saying let's let time equal 0. Well, of course, this was beta 2 times time. At time equals 0, that goes away. That means the intercept of that line is just the intercept, beta naught, which is what we did earlier. That was about 83. Looking at it this way, that's exactly what we have. I mean, all I've done is put this in parentheses. You'll see why here in just a second. So now let's look at time equals 1. When I plug in 1 into here, which is now late, that turns beta 2 on. I call 0 off and 1 on. So of course, when I plug in a 1 for time, that leaves beta 2. So I've got beta naught plus beta 1 light plus beta 2. If I reorder those terms, I can reorder them like this. And this is pretty clear to see. The inside of the parentheses is the intercept, and the coefficient of the continuous variable is the slope. And so here this beta 2 is really just an adjustment to the intercept of the early. So beta 2 represents the adjustment of the intercept that was represented by the early one. Beta 2 is not the intercept of the late, it's the adjustment to the intercept of the early one. That's why we have a reference. In this case, the reference would be the early time period, and the non-reference would be the late period. Again, I can't stress it enough, with the reference, whatever you make to be the reference is what SAS codes it to be 0. In our data set, we forced the coding early to be 0 and late to be 1. So we coded 0 early as the reference, meaning that this intercept will represent the intercept, and whatever is not the reference, that coefficient will represent the adjustment to the reference's intercept. That's what you're looking at here. So again, I've just kind of rewritten that right there. Let's go on to the next slide. We're going to be doing kind of regroupings like this quite a bit, especially when we look at differences in slope. So this is just a model of just kind of another way to look at what we just described. You can see here, remember, the top is the early, and the early is our reference because it's coded 0, and it's just beta naught. And that beta naught earlier was 83. We're going to see that again here on another slide. This right here, this intercept, if we were, notice is at 150, so we'd have to kind of continue these out a little bit more to hit 0, to right about here, where that would be about 83, and this one would be the other intercept. But this is 83 plus negative 12, right? Beta 2 was significantly different than 0. It had a very small p-value, but beta 2 was about negative 2, or negative 12. So that's 83 minus 12, which is about 71, which is about what this intercept will be when we go out, when we make this the y-axis, which is at 0. So just totally consistent with what's in the book. We like it when we kind of look at things from different ways and they all come back together. So that's a very simple concept that once we look at it enough becomes simple, and we want to add on to that foundation. Of course, in any model, we want to check the assumptions. We don't know those p-values are accurate, biased up or biased down, or just straight up accurate unless we've got the assumptions being met. This one I don't see. I love the residual plot. Looks like there's not a lot of evidence against normal distributions here. It doesn't look like there's a left skew or right skew. We can look at the histogram of the residuals again to see that. It doesn't look like there's any increasing, systematic increasing or decreasing standard deviations dependent on the predicted value. I'm looking at my influential plots. Looks like there may be an influential plot. I'm not too concerned about it because I don't have anything in these little quadrants or sextants right there. There's nothing that has high residual and high leverage. This one just has high residual. So you may, if you have time, you might go, and time and money, you might go look at that one. I'm not too concerned about it. Its Cook's D is well below 1. It's above this bar, which is 4 over n. So I'm just, my opinion, I wouldn't be too worried about it. But certainly that's subjective. So QQ plot looks pretty decent. So I like my assumptions, and I'll continue on with whatever else I want to do with the model. We'll get to the conclusion here in just a second. Just kind of want to revamp what we looked at in the past. The intercept here of the top line, the red star represents early. That is an intercept of just whatever this was, 83.46, since that's the reference. And we'll adjust that intercept to get the intercept of the late, which is 83, and then plus this minus 12. Again, this minus 12, this adjustment is significant. If it was not significant, then we'd say that these, since we're forcing the slopes to be the same, we'd essentially conclude, if this was not significant, that there's not enough evidence to suggest that these lines are different. But since the intercept, the adjustment to the intercept is significant, it certainly is evidence that these have different intercepts, and they're being forced to have the same slope right now. So just to give you a quick, we're going to be making a lot of these in our homework. This is just finding the actual equation. The first equation of the reference is always easy. That's just the intercept plus the slope times the light variable. This one is, we got to do a little more work. It's just 83 minus 12 to get the intercept, and I'm forcing the slope to be the same. So those are my two regression equations. You can interpret those from there. We didn't do any fancy transformations, log or otherwise, so that's just straight up. We'll do that here in just a second. In fact, here we are. So increasing light intensity decreased the mean number of flowers by this meadowfoam plant by an estimated 4.0 flowers per plant per 100 nanomoles into meters squared per second. So that's a pretty fancy measurement for light intensity. And notice that our coefficient here was 0.04. We just multiplied that by 100 to get 4.0 flowers, and we had to say it was 100 nanos instead of just 1, which I believe makes more interpretable. 95% confidence interval for that is 3 to 5. And I don't have that shown on here, but you would just simply do the CL-PARM or CLB to get the confidence limits of these parameters out here. Very easy to do. Again, in reg, I believe it's CLB. So you can check that out. Very easy to get those, or you can figure them out by hand, of course. So let's do the other one, beginning with the light treatment for 25 days before, or 24 days, it needs to be fixed, 24 days before PFI. Increase the mean number of flowers per plant by an estimated 12.2. We kind of rounded there to the 10th. With a 95% confidence interval. If we looked at the confidence interval again with CLB, it would not contain 0, of course, because it was significant down here. That agrees with our hypothesis test. We reject the beta being 0, so 0 is not a plausible value. We think it could be as small as 6.7. We're 95% confident that it's between 6.7 and 17.6. And then here's our scope of inference. It was a randomized experiment. We can draw the above causal relationship because the seeds were randomly assigned to each treatment group. Since we have assumed equal slopes, because we have not allowed for the adjustment of the slope, we can assume this difference is consistent across all intensities. So the question would be, can we make that assumption? Can we make the assumption that the intensity affects the flowers the same way for the early and the late stages? That might be something we want to test, and we'll certainly test that next class. Just to finish off this video though here, I wanted to kind of show this. This is, for just kind of focusing up here, this is PROC-REG and PROC-GLM, both of those, just so you can see how if you put it into SAS different ways, you might get something different. This is for reference being early because the time was 0. Notice that you'll get the same exact, whether you use PROC-REG or PROC-GLM, you get the same exact tables. I think they're easy to read like this. If you look at this one down here, PROC-GLM, and you make class time equals ref equals 0, that gives you a table like this. And class is where you put the categorical variable, which we're defining as time. This one actually tells you time with a value of 0 is your reference, because its estimate is 0 here. You don't get any estimates. The time 1, this is the adjustment, and so you can easily see, just like by looking at the parameter estimate table, which value of the categorical variable is the reference. And we can, of course, change that if we made that a 1, and we'll do that on the next slide. Just to show what happens if, remember from the initial data set, you might go back to see it, I had also had a column called timing that wasn't coded 0, 1, it was coded as a word, early, late, which I think is exactly the way that you really want to do this, because your parameter estimate tables are much more interpretable. You don't have to remember if early is 1 or 0 or late is 1 or 0. It just says it right there if you recode one with a string variable instead of telling SAS that your number should be interpreted as a string. Now, quick note, when you use PROC-REG, you have to use 0s and 1s. It doesn't have this ability, right? PROC-REG doesn't have this class statement. So you can only use this nice, labels, labeling column in PROC-GLM. But it works the same exact way. Instead of calling it 0, I'll call it early. It says timing early. I can clearly see it's my reference. And that late has a smaller estimated intercept because that is significant. So let's see, we could have done it the other way, and you might end up doing it both ways if you want both lines. This again is just showing PROC-REG and PROC-GLM will give you the same thing if you treat that 0 and 1 as a numerical entry. However, if we use PROC-GLM and tell it, hey, let's not let the ref be 0 this time, let's let late be the reference, or the reference to be 1. And clearly now notice that everything that, that the intercept is 71 here, because that's the intercept of the reference, which is the intercept now of late. In order to get early, we have to add 12 to that. And so now we can see that time 1 is the reference, that's late, and the adjustment is 12 to get back to the intercept for early. So it's just switch signs. It's very common. Over here, it's just saying, hey, this is much more descriptive. I call it late in the timing variable. I'll just call that late. Everything that has a late will be labeled in SAS as late, and everything that has early will be labeled in SAS as early. I can see that this is the reference. Now this is the late. Again, it's 71 for the intercept for late, and it's a 12 additional 12 points to get to the early intercept. Exactly what we saw on this side. It's just a different way of labeling it. I think these are much more clear labels to whoever's reading it. Notice in all of these, the intensity is the same. We're going to underline that for our next set of videos. But for now, I'd like for you guys to try one. So you can take this PowerPoint presentation should be available to you on Canvas or whatever learning management system we're using. So, so go ahead and try to find this 9A grades and perform this, and you should be able to check the solutions are here, and then I've got another problem for you, and the solution is there. So go ahead and try those, and we'll pick back up with the duck example. So I'll see you in a bit. Nice work. Hello and welcome back to Chapter 9. This is multiple linear regression. We just covered how categorical variables we can fit a model to where the categorical variables can affect the intercept. We will get to how it could actually allow for flexible slopes as well. But first we wanted to interject another huge use and tool of multiple linear regression, and that is accounting for possible confounding variables. This is going to be a very useful thing as we move into the rest of this semester with big data, with other data science topics. Confounding variables are a huge concern, and multiple linear regression allow us a way to account for some that we may be able to identify in our experimental design. So these are, of course, ducks, and these are much larger animals, elephants. And our idea is we want to look at their gestation period, that is how long a female would be pregnant before giving birth, the brain weight, which is just simply the weight of the brain, the body size, and the litter size, how many offspring they'd have in one litter. So we would like to see how that might work. So our question of interest here, which is always where we want to start, is we would like to test to what extent gestation length and litter size are associated with the brain weight. So as litter size goes up, does that imply that brain weight may go down or tend to go down? As litter sizes go up, or gestation length, or either one of those, are they positively or negatively linearly correlated with brain weight? That's our question of interest. So we can look at our data here. We can see how I've kind of labeled it. This is the SAS data step. We've got the brain weights in the first column. We've got the body weights, the gestation lengths, and the litter sizes, average litter size for 96 different species. And so what we would like to do is to run a multiple regression. But first, of course, we want to, after looking at the question of interest, we would like to plot the data. Always want to look at it. We can get a lot of information just by looking at the data. And clearly we see that body weight, actually these are the logarithms. So I kind of skipped a step in here. You'd first look at, of course, the raw data, and it looks like a logarithm, a log-log transform may help you out quite a bit. And clearly this is very strong evidence of a linear relationship, pretty strong linear relationship between the log of the body and the log of the brain weights, the log of the body size and the brain weight. And then we look at some of these other variables though. We look at log body and log gestation and also see a strong linear correlation. And we look at log body and litter size, and we see somewhat weaker, but maybe some evidence of a negative correlation there. We call this multicollinearity. But what we could be looking at here is a possible confounding variable, because if I look at log gestation and log brain, it's a very important topic. It looks like there's a strong linear correlation between log gestation and log brain. And if I just ran a simple linear regression, I would expect to see a significant positive coefficient. But noticing that log body and log gestation are highly correlated themselves, highly positively correlated themselves, this is telling us that it's tough for us to get some animal with a high gestation that has a low body weight. Most high gestation animals have higher body weight, tend to have higher body weight. And so if that's the case, then as I look up here, is what's driving this positive linear correlation, is what driving it gestation, or is it simply the fact that for high gestations I also have high body weight, and that's what's really causing or related with the higher brain weight? In that case, body weight would be a confounding variable. Again, as gestation gets bigger, it looks like brain weight gets bigger, but as gestation gets bigger, so does the body weight. So is what's driving this relationship body weight, or is it truly gestation? What we would like to do is see if gestation, remember this is all about explaining variance, explaining the variance in the brain weights. So what we're going to essentially do is see if gestation explains a significant amount of variance after the log body weight has explained all the variance it can in the log brain weight. So how do we do that? We can do that with multiple linear regression. So again, we would like to see if gestation, length, and litter size are associated with brain weight, but after we have controlled for this confounding variable we think might exist by looking at the data or just thinking about it of body sizes. So, so you can read this, but that's all what we've just talked about. We'd like to look at each one of these variables individually, gestation and litter size, and see if they are significant in their own right after accounting for body size. And then we don't have to worry about the confoundingness of body size with respect to those two variables. Multiple regression is a great tool for this, very easy to use. We can fit exactly, so we'll just kind of, I'll just put all of it up here. So basically what we're looking at here is this column is the non-log. It's just the linear model. It's just a simple linear model. We see that gestation is highly significant, but looking at the assumptions here, we don't even have to look at the panel of residual plots. It looks like there's increasing standard deviation, and it looks like there's a little curve trend to the data. So instead, we try, and this is just the SAS code if you want to follow along, to do a log transform. And when we do the log transform, we see that the relationship between the log gestation and the log brain is the residuals are much more normally distributed. We would look at the panel of scatter plots for this, but I would tell you that when you looked at those, you will see you would not see a lot of evidence against a normal distribution of the residuals. This is a great looking scatter plot. Looks like constant variance all throughout, or at least no evidence against really significant departures from that. It looks like a pretty well fit. The assumptions are met for simple linear regression there. And so I have more confidence in this estimate of 2.2 than I do in this estimate of 3.4, a considerably different estimate. Both are significant, but of course, in the end, if we're going to interpret these estimates or even use them to predict, we'd like them to be as close to the true ones as possible. And certainly this is going to give it to us. So first, this is us deciding that, yeah, it looks like we want to deal with a log-log model of this. And so we're going to fit this. The log brain size versus log gestation and log body. So this is looking at log gestation, but throwing log body into the model. And when we do that, we are accounting for any effects that the log body would have. And it shows that after log body has explained the variance that it's able to, log gestation is still significant. So we don't have to worry. Notice that its coefficient has changed, right? It's went from 2 point something to 0.6 something, but that it is still a significant variable, albeit holding body size constant, and has a little bit of different relationship than we thought in the first, but it's not confounded anymore with the body. And then I just threw this in here, I believe. Yes. So just in case you're wondering, if you put in log gestation and log body, or log body and log gestation, it doesn't matter the order in which you put the variables in. You're going to get the same estimates with the same results and the same intercepts, of course. So that's just showing you don't have to worry about in which order you're putting those in. Okay. So great. So we look at the assumptions of this model. It looks like we may have a little bit of evidence now when we put them both in of non-constant standard deviation. Not too bad, or they certainly look normal. QQ plot looks great. I'm not super happy with this. There are more observations out here, it looks like, so maybe it's filling out a distribution. But this is something we don't proceed with caution. We may want to choose an alternate method. It's not a super serious departure, but it's something to be concerned about. Not too many, not really any threat of severely influential observations. Again, I'm looking in this quadrant, which is really a sextant. But this would be high leverage and high residual, and this would be high leverage, high residual, and there's none there. There's a couple of high residuals, a few high leverages, but none of the both. So although these are above the very conservative line that SAS puts out, they're all considerably below 1, and nothing I would be really worried about. Okay, so what do we have? These are, again, our residual plots. I do see a little some evidence against equal standard deviation, so I might want to proceed with caution with this. But this is what I've written down here, so you can check that out. But that is our method so far. We can conclude, though, these are still unbiased estimates. These estimates here are unbiased estimates of the log gestation and log body, and we can reasonably conclude that, and as we will here in a moment, we'll reasonably conclude that log gestation is a significant factor in predicting brain weight and is not confounded with body with these coefficients. So there we have it. What about liter size? Same idea. Here it is with liter size. Notice it's a -2. Here it is with the body. It is showing that it's not confounded, that it's still a significant predictor, but its coefficient is significantly smaller than, or significantly closer to 0 than what it was otherwise. So it's no longer confounded with body, but we get a better estimate of what it should be, of its real relationship, holding body weight constant. So that's essentially saying, hey, give me a whole bunch of animals with the same body weight. Now let the litter sizes go up and down, and we can see for that particular subpopulation of body weights how litter size is related to the brain size. All right, and of course we did the log-log model. So here are our models, log and the log, on both sides of the equation. We're going to check our assumptions. Same kind of concern with the standard deviation, but certainly no problems with normally distributed residuals. Still same thing, not a lot of concern with influential points, but we might want to mention this in our analysis that there may be some concern with a slight break in the assumption of equal standard deviation. But remember, George Box, all models are wrong. This certainly doesn't look like a serious departure, but one that you might want to mention and proceed with caution. So as a conclusion, we've got both our parameter estimate tables up here. We can, I'll let you kind of look over these. These are just definitely something you want to review. These are the interpretations of a log-log model. Remember, we're going to take the coefficient now to 2 to the coefficient, and then this is an estimate of the multiplicative change in the median. And so, so this is 2 to the 0.668, so 2 to this coefficient and 2 to that coefficient means a doubling in the litter size is related to a 2 to the point for litter. What is litter size? A doubling in litter size is associated with a 2 to the -0.538, which is a multiplicative change of estimated to be 0.689 in the median of brain size. And so you can tell that that's associated with a 31.1% decrease, which could be very useful to biologists or whoever's looking at this problem. Awesome. We've accounted for possible confounders. If we thought we had more confounders, we could put those in the model too, and then interpret our model accordingly. So that's awesome. Great work on that. There's a couple of more practice ones in here, so check out this PowerPoint. You can do those data sets should be available to you on the learning management system, and I'll see you next time. Nice work. Welcome back. And for the next installment of multiple regression, we're going to pick up where we left off. And remember from last time we talked about the reference category. And we used the metaphome example, and our categorical variable was early, late, which was the time variable. It had 2 levels, early and late. And we had coded manually an indicator variable for early, which was 0, and late, which was 1. Inside of SAS, we use procreg, that automatically defaults to making early the reference category. With procglm, you're a little more flexible. This code that I have here is showing kind of where we picked up last time. It's being redundant because that would be, if we didn't put this class statement in here, the reference would still be early because it's coded 0. But just to show you, inside of procglm, you can tell the class variable holds what the categorical variable is, and it tells SAS to make indicator variables for the levels of that variable. So this one's saying, okay, SAS, take everything that's a 0 and make an indicator variable and code that as 0. This other variable, I'll have to describe to you real quick, is a variable that I made inside of SAS called timing. It's in the data step. So there's a column called time and there's a column called timing. I've made everything that's a 0 got an early, and everything that got a 1 got a late. So, so that's what the class variable does. Notice in this one I'm only referring to time. So that is, that's where we're at. So intensity and time, that's the one. So now what we're going to do next is, don't forget your solution at the end of a procglm statement. And here we go. Now notice on the other one here, notice the difference that I have said, okay, well the time, I'm still going to call that ref1, and notice that the timing column then is late. Again, it might be a little confusing here. I just put this timing variable in here to show you. I'm about to use it. It won't be as confusing when you see what's going on down here. So so let's just look at the time variable right now. It's ref equals 1. It's going to tell SAS to code all the ones as zeros, because we're going to make the 1, it's not the number 1, we want it to mean late. So it's going to take time, and it's going to make an indicator variable and code that indicator variable as a 0 if it sees a 1, and a 1 if it sees it's a 0. Is that confusing? Yes, which is what I'm about to show you why I'd rather use this timing column that I created. But as you can see, all that does is switch. That's negative 12, that's positive 12, because it's just an adjustment to the slope like you saw in the last one. So let's see why GLM can make this a little bit easier. If I go ahead and code, so this is data mf, set mf, time equals 1, then I'm going to make a separate variable called timing, and that'll be late. And if time equals 0, then I'm going to make a separate variable called timing and make that early. So that is what's happened for these last ones here. So there's the code, and there is the solution. This one says ref equals 0. Notice now I'm using the timing variable. And so it's going to have these nice little labels down here. Instead of saying time 1 and time 0, it says time late and time early. So I don't have to remember what the coding was. I can code it in the data step and then have it reflected on here. So this is just a couple of ways of all doing the same thing. You already know how to interpret these from the last session, or from 2 sessions ago, from when we talked about the flexible slopes, flexible intercepts. Now we're going to talk about the flexible slopes in this video. So there we have it. Just a couple of ways of doing the same thing. Let's continue. So this is what you see from the book. It recodes them. Sometimes the book uses light, and sometimes it uses intensity, and sometimes it uses day 24, and sometimes it uses early. So this is the one where it just calls it light, but that's the same as intensity. And notice when I don't distinguish between the timing variables, I just have one line. I have forcing the intercepts to be the same and the slopes to be the same. So remember, after that, then I can introduce a categorical variable called day 24 here. That's their code for saying this is a categorical variable in day 24, which is early. If you go back and look at if you remember the actual experiment, that's early. So you think of day 24 as early and light as intensity in our naming scheme. So when we do that, it's forcing the slopes to be the same, but the intercepts can be different, as we've seen. The intercept is either beta naught for the reference category, or it is beta naught plus beta 2 for the non-reference category. And that's when there's only 2 levels. But now what we'd like to do is make the slopes. We want to see if the relationship between the x and y is the same for the 2 levels of the categorical variable, which could be extended to 3, 4, or 5, as you'll see in the homework. So so here we go. How do we do that? And that's what's so cool. This is just an algebraic rearrangement of the terms. But here we have beta naught plus beta 1 light plus beta 2 day 24, and then we interact the continuous and the categorical variable. That's day 24 in light. So when we do that, and of course we estimate another coefficient out in front of that. So what we do is this term right here allows us to have an adjustment to the slope. This this beta 2 was an adjustment to the intercept. This beta 3, as you can see here, will be adjustment to the reference slope. Be careful, beta 3 is not the new slope, it's the adjustment to the reference's slope. So this bottom number here, this bottom one was chosen to be the reference for this example. Its intercept is beta naught, its slope is beta 1. Beta 2 is the adjustment to beta naught, it's the adjustment to the reference's intercept, and beta 3 is the adjustment to the reference's slope. And our goal will be to find out if beta 2 and beta 3 are significantly different than 0. Because if they're equal to 0, or if they're not significantly different from 0, right? If beta 2 is not significantly different from 0, that's saying the intercept is beta naught, which means that there's no reason to believe that these 2 lines have different intercepts. They will, of course, have different beta naught hats, but we're asking is if the beta naught hats were different enough to say that the actual beta naughts, the actual intercepts of those 2 lines are different. Maybe replay that a couple times and really make sure what I meant by that. Of course, in the samples, the beta naught hats are going to be different and the beta 1 hats are going to be different. The question is in any hypothesis test, are they statistically significantly different? And that's our whole goal here. So that's what we're seeing. This is the algebraic breakdown of how it works. I think this really kind of puts it into perspective. Notice that that's the equation. If I factor out, here is a light, right? There's light in this term and there's light in that term. That's a variable. Light is a variable. So I can factor that out, and if I do, I'll be left with this light on the outside and beta 1 plus beta 3 times early. There's light. And then notice that I just grouped beta 0 and beta 2 together because these are the terms that look at the intercept. Those are not concerned with the continuous variable. Slopes need a continuous variable, and our continuous variable here is light. Early is not. Early is the categorical, so I group all these non-continuous variables together. That's beta 0 and beta 2 early. That goes into the intercept. And then I factor out all the terms that have a light in it, and this becomes the slope. So you can easily see here, for early, when I plug in a 0, because early is 0, when I plug in a 0 here for this variable, that's going beta 2 is going to go away, and so the intercept of the early is 0, is beta 0. And then when I'm dealing with the early group, I plug in a 0 here, and it's just beta 1. But when I'm dealing with the late group, I put a 1 in here, and that's beta 0 plus beta 2, and that's beta 1 plus beta 3, and then of course that's times light. So now the intercept and the slope depend on the time. So great, so now we can see algebraically and heuristically how we can change these slopes and the intercepts. So basically, I'll just put everything up on here. So this is where we started. It's a simple linear regression. That was chapter 7. There was no way to have adjustable intercepts or adjustable slopes. It's just all the same data, so we get one line. Then in chapter 9, in this video that we just looked at before, this is time with no interaction. By interaction, I mean interactions between the continuous and the categorical variable. There is no interaction there, so it's forced to have the same slopes, right? Beta 1 is the slope of this line is beta 1, slope of that line is beta 1. You can see that right here. But they're allowed to have potentially different intercepts, and we're going to check to see if beta 2 has a small p-value, if it's insignificantly different than 0. And if it is, then we'll say that that's a significant adjustment, and these two lines, the evidence suggests these two lines have different intercepts. Now we'd like to be able to do the same thing for the slope, so we simply add an interaction between light and day. That'll put light here so I can factor that out. Remember, I can factor that out. I get beta 1 plus beta 3 for the slope. For the reference, it's just beta 1. And for the non-reference, it's beta 1 plus beta 3. If beta 3 is significantly different than 0, we'll do a hypothesis test on that. If it's got a small p-value, then we'll conclude that the slopes are different, and we'll have an estimate, and we can get a confidence interval for just how much those two slopes are different. Awesome. For the beta 3 is the difference in those two slopes. Okay, great. So once again, there's that picture. We'll just keep going. So here is the question. In this particular example, is the separate slope model appropriate? Do we need to account for different slopes? And we look at this one, and this is the actual data. And it doesn't look like they look pretty darn parallel even in the sample. But as it is, we go through the parameter estimate table. This is the intercept. That's the estimate. That's the p-value. This is the slope of the reference line, and we can see here that our reference is late, and we've seen that. Here's timing, so we're choosing our reference to be late. Cool. So this is a little bit opposite. This is the other reference that we did earlier, just to show the contrast. So right now, late is coded as 0. So this is the intercept for late, whereas you can see late is the bottom line. That intercept would be about 71. This isn't the y-axis. The y-axis is actually over here. When the intensity is 0. So the intercept is 71. The intensity of the late line is negative 0.04107. And so that's the intercept, and that's the slope of the reference line. Now for early, how do I get the early? I have to add 11.5 to this intercept. So this one's about 82 or 83, whatever we found earlier. And then now I have an adjustment to the slope. So the adjustment, these two slopes look pretty similar, but they're actually somewhat different. The slope here for the early line would be negative 0.04107 plus 0.0012. And you can see that looks pretty close to 0 with respect, pretty small with respect to that initial slope. So that would be the adjustment. This early line has a slightly less negative slope because I'm adding this 0.0012 to it. But then we say that's not much of an adjustment. Is that statistically significantly different than 0? And we say, I don't know, let's come over here. Well, there's our standard error. I divide those two. I get a t-statistic. I look it up, 0.9096. Look at that t-statistic. So that's really close to just really no adjustment at all. It's certainly not statistically significant. So the null hypothesis is here that the beta 3 equals 0, and the alternative is that beta 3 is not equal to 0. We fail to reject that hypothesis. The null that beta 3 is equal to 0, we fail to reject that. And so we conclude that there's not a statistically significant difference between the relationship of intensity in flower production, which is the slope, for the early group and that received light treatments later. So that's the later was after the PFI. And I put my p-value down there. We could certainly add confidence intervals on top of that as well, simply by adding for ProcGLM CL Parm on the end of that. So let me quickly go through an example where interaction does matter. Boom, so let's do it. Ready? Here we go. This is an example. Data set records the amount of cash someone makes. That's the cash, that's like their income in thousands, and the amount of money they give to charity based on the importance. So this is the bigger the number, the more important they feel the charity is. They ranked it. Each subject attributes to the charity. This other variable here, this variable charity is how much they actually donated in dollars. This is in thousands and this is just in dollars. So that's how much they actually donated in dollars, and this cash C is a variable that indicates that they make, well here it is, indicates that they make more than $45,000, and that should be a K there for $45,000, and 0 is that they make less than or equal to $45,000. So there it is right there. Cash C is a variable that indicates if the person makes over $45,000. So that's what we might like to do. So we want to construct a multiple linear regression model in which the mean charitable donation depends on linearly on the importance of both charity and income groups. Allow for possible slopes and intercepts. So we want to build the model that allows for that flexibility. So there's our model. Of course, we need importance, and that's our continuous variable. Cash C is our categorical variable, and the interaction so that we can allow for different slopes. The cash C variable here is here to allow for different intercepts. If you would, maybe pause the video for a second and rearrange these variables, rewrite this equation so that you have just the intercept in parentheses and just the slope at the end. So that'd be a good one. Come back to class, or you can shoot me an email and ask me if you got it right. But that's the idea. So, so we run the regression, and here it goes. I'm going to say, hey, let's make ref equals 0. Of course, I've already coded as 0, so that is a little redundant. That's what it would have done anyway, but just so we can see what the class variable does. I need the solution, so don't forget slash solution when you're in ProcGLM. And this little bar here, this pipe, the pipe means interaction. So it's going to do the interaction between cash C and imp. You could have done cash C imp, and then over here, a third one, you could have done cash _ C star imp. But this does it all for you. So you just put a pipe in there, and it does that full model. It'll fit this model. Okay, great. So we do that, and we kind of interpret it. We say, hey, okay, it looks like cash C0, so the people that make less than $45,000 a year are the reference, and those that make more are the non-reference. And so for the people that make less than 45,000, their intercept is 48. So here's the blue line. You can see that that's right about the intercept, right? That's 10, 8, that's probably 6. So the actual 0 line is out here somewhere. SAS doesn't necessarily start at the origin. So the intercept is about 48, and the slope is about negative 0.88. You can see that that blue line has a slightly negative slope. So one question would be, is that slope significantly different than 0? You can say no. Look at that. That 0.3569, you're testing the null that, in this case, you're testing the null for that line that beta 2 is equal to 0 versus the alternative that it's not equal to 0. And from this, oh, there's my up there. So this is the one for beta 2. Sorry, this is the one for beta 2, and this is the one for beta 1. So, I'm sorry, this is the one for beta 1. Yeah, this is the importance coefficient. So this is what we'd estimate for beta 1. And this is what we'd estimate for beta 2. So let's look at that one real quick. Let's just do the intercept one first. I kind of jumped off to this slope one. The intercept says, hey, is the for the people that make more than $45,000, is the intercept different? And surely it looks like it is. This intercept's going to be over here somewhere. This red one's going to be down there somewhere. So it looks like they're different, and sure enough, this is suggesting that yes, it is different. Again, the null is that beta 2 is equal to 0, and the alternative is that beta 2 is not equal to 0. We reject that assumption that beta 2 equals 0, and this is our best estimate of beta 2. And clearly we can see that that this red one would have a smaller intercept if we extended it out to the y-axis, and that's the estimate of what it was. If we want a confidence interval for that estimate, then simply put CL parm on the end here, and you'll get some confidence intervals for that, which is what you should do. So going down here now to the importance, notice that for the reference, which is 0, that's negative 0.88, slightly negative, but it's saying that's not even significantly different than 0. That might as well be a horizontal line. Doesn't look like for the people that make less than $45,000 that there's a real relationship between the importance of the charity and how much they give to the charity. Maybe they've got more uses for their money that are more pressing than to give to charity if you're making less than $45,000. That's a speculative answer, but you're trying to make stories to this thing as you go along, things that make sense to the rest of what you know. So then we'd say, okay, well, let's see, this slope certainly looks different. For one thing, it's positive, and it's pretty positive. So I say, okay, well, what is the adjustment to this slope to get the people that make $45,000 relationship, to get their slope? You have to add 4.14. And we say, that seems like that should be pretty significant, but let's run the hypothesis test. Okay, so let's run null that this beta 3, this right here, this 4.147 is beta 3. It's the estimate of beta 3. So let's run a hypothesis test. The null is beta 3 equals 0. The alternative is beta 3 is not equal to 0. There's my p-value. I reject the null that beta 3 equals 0, and that is my best estimate. It's probably not actually exactly beta 3, so I can get a confidence interval out here, any confidence you want. Again, by putting CL parm in here. So that's that. That's an example where the charity actually meant something. The charity meant something. Of course, the charity meant something. That's the one where the adjustment to the slope actually was statistically significant. So just to kind of finish this off, what you can do with this is write down the actual models. You can write down the actual regression equations. So this will really kind of help put it together for you. Kind of come through here. If I want to find the charity for, which one is this one? So we have here 48. It looks like my reference was 0. So this one, this line right here is for the people that make more than $45,000. Because you can see I'm actually putting the, actually this is just the equation. Sorry, right? 48.10 minus 27.68, that's the beta 2, minus 0.8803, that's this beta 1. I just flipped these, but that's the coefficient of the importance plus beta 3, 4.15 times cash dot imp. Then I can rearrange those, is what I asked you to do earlier. Rearrange those so that the things that do not have the continuous variable, things that don't have importance in it, I put those as the slope, as the intercept. And the things that do have the importance in it, that's the continuous variable, those are the slope. And so this is the adjustment. So if you wanted the one for charity, let's do the, I'm sorry, if you want, they're both for charity, again, if you wanted the one for the people that make less than $45,000, it's the red one here. That's the, let's make sure that's right. That's right. That's the one that I have in red down here. That is 48 minus 27. 48 minus 27 should give you 20.41 plus 3.27. How do we get that? That's the negative 0.88 plus 4.147. So you put both of those together and you get, that is the one for the, sorry, dang it, that makes better sense. That's the one for the people that make more than $45,000. That's the one that they make more than $45,000. That's this red line. And we know that because for the people that make less than $45,000, that's this blue line. So you just, for the reference, it's easy. You just pull off the intercept and you just pull off the slope So there's the intercept, there's the slope, and that's very easy. So whatever the reference is, you can pull the regression equation very easy off of there. And then you do the subtractions for the adjustments, and you can get this one, which is for the people that make more than $45,000. If you've been thinking about it, you can actually just change. You could put reference equals 0 and make this line. And if you didn't want to do this subtractions and adjustments by yourself, just make that ref equal 1. Just make that ref equals 1 and refit the model. And this intercept here will be 20.41, and that importance there will be 3.27. So that's a very easy, quick way that you can actually get SAS to do the math for you.